Okay, so now we should be recording. Everyone should see a flashing red light in the upper left-hand corner of their Zoom screen. So we are on, and I will hand the floor over to you guys and let you tell us what you've come up with.
All right, awesome. Well, first off, thank you everyone for being here. We're group 3, and our design project for this semester is the UC GAM system. This is the unmanned cell growth and monitoring system. And our group is comprised of Cameron Anderson, Devin Cornair, Jeffrey Ho, Alex Kuchalakos, Richard Missoula, Abraham Ortiz, Max Rosen, and Khalil Sabawi. And so in these first 2 slides, we're just going to be giving a brief overview of how this system works and the full operational rundown as if you were the technician or the lab assistant. So on this first slide here, we have the overview of the enclosure. Prior to operation, the user would open this the front panel right here, and you can see that it has a rubber gasket which is sitting against a aluminum cutout and is clamped down with 2 clasps, similar to how sandblast machines work, with the rubber seal insulating it. On that panel, there's a sheet of acrylic which is useful for viewing inside the container, and on top of that, via magnetically attached strips, we will have a plastic cover that goes on top, which is made of a very dark but transparent material. And that was we attach that whenever we're going to be doing ODFI measurements. So the first steps of this this process would be they'd open the lid, insert whatever well plate or conical tube they have, after swabbing it with bacteria, of course, and then they would close the lid and move over to the bottom left corner of the front enclosure, which is the user interface system. Our user interface system has a LCD screen as well as a D-pad for navigation and a red emergency stop button. On this D-pad, they would be selecting the temperature that they wish to run the experiment at, as well as the mixtures of gas compositions that they want. On the front panel to the right, you'll see a waste reservoir drain. This was a feature that we added in order to reduce the possibility of contamination by trying to drain externally any fluids inside that are just sitting there, because we figured that it's probably not a good idea to have bacteria just sitting in a container that is even somewhat exposed. On the left, you see our gas intake system. This is connected to 5 tube clamps, and those are solenoids, and the solenoids will enter the box and be circulated, which will allow ourselves to get a good mixture of gas before they are vented inside using 2 fans. And then on the top of our enclosure, you see the cutout in our polyurethane foam, which is for insulation, but that cutout specifically is where our coolers are, which are allowing us to cool the system down. Okay, so we're going to go to the next slide now. All right, so now we're inside of our system, and you can see all the components we have here. So the first step, aside from setting everything up, is the technician would be placing the well plates onto that central clear table you see there. Now our system is designed for either 3 well plates or 3 racks of conical tubes, or any combination of the 3. So for the purposes of this explanation, we're going to say that we're using 3 well plates. So they would place the well plates onto the table, pre-swabbed, and then they would step out and close the door, at which point they would hit the start button and select which well plate that they wish to proceed with. And then the fluid handling system would activate and move over to the first bin, which was one of those white bins you see there. It would start extracting media from that bin using the syringe pipette system that we have. And that pipette is a 1250 microliter pipette, which is about the max volume we could get. It would extract the media, then go over to the well plate of desired and start administering the media to the different wells. It would repeat this process, of course, until the pipette is empty, and then go back and refill however many times needed to fill up the well plate. And this process is the same for the conical tubes as well. Once it is finished delivering all the liquid that it needs, it would empty out any remaining liquid into the waste reservoir, and then move over to the middle waste bin and eject the pipette tip using our tip ejector system that we'll discuss later. From there, we will conduct an initial set of ODFI measurements just to get a baseline, and noting that once we've ejected the pipette tip, there is no issue with clearance, that the ODFI can go down and scan all the wells properly. Once it has done that, it will activate the grow lights, which are underneath the clear plastic table that the well plates are sitting on. And our lights are arranged in a sequence of white and amber lights. The white lights would be for growth, and then the amber lights would be turned on, and of course the white lights off when ODFI measurements are to be performed. This is to prevent harmful rays. It's to gather a better ODFI measurement and also prevent any harm. Okay, so once the ODFI measurements are complete for that cycle, and then the well plates need to be shaken, our gripper system will move over and pick up the well plate and transport it to our shaker table. Currently in this picture, we see the conical tubes sitting on the shaker system, but I mean, they wouldn't be there. So we would move the well plate into that shaker system with the gripper system, which we'll go in more detail later. And then the gripper system will move over to the left-hand table, pick up a lid, and place the lid on top of the well plate. Now, our gripper system is designed with 4 tabs that are just spaced out enough to contain the lid. So by adding the lid, we will be securing the system down and prevent any spillage while the system is shaking. Once the system is finished shaking, it will take off the lid, remove it, and place it back on the second table, and then pick up the well plate and move it back to its original spot. And then this process will continue. Notice on the back walls we have our 4 heaters, as well as a fan to circulate the heat. And then in other slides, we will show you the rest of our cooling system and also go more in depth into the heating system. But yeah, so that is the general overview of how our system works. Also, if the client is interested in doing cell evolution, a setup we encourage would be to have 1 well plate filled with the bacteria that you wish, to run the experiment, and then when you wish to evolve those cells, you would, using our pipette system, extract the cells that were not desirable and empty them out into the waste reservoir, and then take the healthy cells and migrate them to the next well plate, at which point this cycle can continue and repeat until all the well plates are used up. All right, and we're going to take it to our next slide.
So we were designing this microbioreactor with 3 main goals in mind. We wanted to reduce the complexity so that anyone could set it up with minimal training. We wanted to still be effective by meeting the customer needs, in which we designed multiple different independent subsystems to meet these needs, such as a shaker, an ODFI sensor. The gripper was needed to move things from the table that was over top the LEDs to the shaker. And we wanted to reduce cost at every step of the way, whether this be manual assembly, manufacturing costs, or even taking off-the-shelf parts and making them ourselves. And we could go to the next slide.
Hey everyone. So the overall structure really has 2 main components that consist of it. The first is the actual frame itself, which is composed of aluminum 80-20 extrusion. And there really are 2 main reasons that we decided to go with 80-20. The first is that the 80-20 allows our 3-axis gantry to translate directly on those rails without having to make any modifications to the frame. And so our gantry actually uses these wheels that are custom designed to slide into those 80-20 grooves. And so we didn't have to make any modifications, which of course saved money. The second reason we decided to choose 80/20 was to keep the assembly simple for the customer. The overall structure is pretty large, and we obviously didn't want to ship it fully assembled. And we also didn't want to assume that the customer had an engineering background. So that kind of drove us to design with ease of assembly in mind. With the 80/20, all the customer would really need to do to assemble the frame would just be to insert the T-nuts, the angle brackets, and the appropriate fasteners, and then secure it in place. The second part of the overall structure is the 3-axis gantry. And so the 3-axis gantry is powered by 5 different NEMA 17 precision motors that in turn drive 5 lead screws. And so with a maximum angular speed of 3000 RPM and using lead screws with 16 threads per inch, we can achieve a maximum linear translation speed of about 3 1/8 inches per second. And you can see on the side, there's a step-by-step time breakdown of the minimum times it would take to process 384 wells. And so including the time it takes to dispense and refill the media, as well as perform the ODFI measurements, the total minimum time it takes to process 384 wells is just under 6¼ minutes. And so you can go into the next slide now.
So for the fluid handling system, it utilizes a syringe pump design as it was the most cost-effective and simplest design to be used to meet the accuracy requirements of the system of the 0.1 microliters. For the stepper motor, it linearly actuates a piston plunger within a cylinder to withdraw fluid when it's retracted upwards and dispenses it when it's linearly actuated downwards. For the particular stepper motor chosen in this system, it has a step size of about 1.524 micrometers. And this step size is small enough to produce a max plus or minus dispensing volume accuracy of 0.097 microliters. And this value is determined by multiplying the step size by the cross-sectional area of the cylinder, assuming that the accuracy of the motor is determined by its smallest step size achievable. It also achieves the 300 microliter per second flow rate by having a max flow rate of 302 microliters for this system. And for this flow rate to be achieved, the linear actuator pushes the piston plunger down at a velocity of 4.75 times 10 to the negative 3 meters per second, and paired with the cross-sectional area of the 9mm diameter cylinder, it is able to meet this flow rate requirement. And with the max required flow rate and the use of a pipette tip with a 0.71 millimeter diameter opening, the fluid is dispensed at a velocity of 0.76 meters per second at the pipette tip at this maximum flow rate. And this fluid velocity at the opening of the pipette tip gives a laminar flow with a Reynolds number of 604, assuming water is used for this study, which is well below the turbulent flow criteria. And this laminar flow out of this pipette tip would minimize the amount of aerosols produced in the system as much as possible to prevent cross-contamination into other well plates during a dispensing operation. And a motor controller is used to control the amount of steps actuated in the motor, and a calibration process would be done beforehand to determine specific volumes of fluid dispensed per the amount of steps moved by the motor. And this would allow the system to meet the precision requirements needed as specified by the customer needs. And then moving on to the waste management of the system. So to meet the cross-contamination requirements, disposable pipette tip system is used. The fluid system moves to a rack of new 1,250 microliter pipette tips at each operation and picks up each tip by moving down and picking up a new pipette tip by a friction fit with the O-ring on the nozzle of the system. And when the dispensing operation is finished, the used pipette tip is dispensed by the pipette tip extractor plate, which pushes the used pipette tip out of the nozzle and into the waste bin in front of the system, which is disposed of later when it is full. And For operations when waste media needs to be taken out of the system, the ability for the fluid handling system to withdraw fluid allows waste media to be withdrawn and transferred to the fluid waste reservoir, which is also in the front of the system. And this reservoir comes attached with a nozzle on the outside of the system to allow users to remove the waste media without need to open the bioreactor and risk air contamination from the outside. And that'll be all for the fluid and waste management system. And we'll move on to the climate control of the system.
Hello, my name is Khalil Sabawi. I was responsible for the climate control subsystem along with Abraham Ortiz. We decided to go with thermoelectric Peltier heaters and coolers, mostly because of the low maintenance they have and the longer lifespan. And additionally, Peltier heaters are very efficient, as you can see from its coefficient of performance. And while the coolers are not as efficient, these particular ones we've selected are very low cost. In addition to that, the Peltier coolers allow us in our system to have very uniform heating. And we felt as if we went with a different type of cooling system, that would counter some of the benefits of the Peltier heaters, such as low maintenance. So if we can go to the next slide. So how our system works is essentially that heaters will be attached to the side panels in the interior of the system near the bottom. They will be attached via an adhesive. And then attached to these heaters will be heat sinks that are also going to be attached via a thermally conductive adhesive. There will also be a fan connected to the side of these heaters that will blow air through the heat sinks that will heat up the air, which will cause the hot air to rise, and then cold air will fall down and be blown back into the heat sink to be heated up. This will create a uniform heating effect, which will, allow the system to be heated equally among the entire experiment. So in order to ensure that we had enough heaters, we calculated from the product's website how much heat was provided. As you can see, it was 120.3 watts of heating. Then we multiplied that by the maximum time allotted, which was 15 minutes, to give us the total amount of heat provided within that time span. We then calculated how much energy we would need to heat up the entire system. We took into account the heat loss from our installation. And we also took into account the mass of the air, the mass of the wet plate, and the mass of the entire assemblies, and multiplied them by their respective specific heat values and the change in temperature. We then divided the total energy needed by the energy provided by a single heater, and that gave us 2.81, or rounding up, obviously, will give us 3 heaters. We decided to go with 4 heaters to further reduce the time. As it currently stands, based on our calculations, we could heat up the entire system to 70 degrees Celsius in around 10.5 minutes. The only other calculation needed was to determine how large our heat sinks needed to be. Our heat sinks, we got them from as an off-the-shelf component. So there was a set predetermined area. So we needed to calculate how many of these heat sinks we would need per heater. In order to do this, we just rearranged the convection heat transfer equation to solve for area. We used the convection coefficient for forced air and the change in temperature to calculate how much area would be needed, and then divided by the area of each heat sink, which per heater would be around 5.68, or rounding up, we would need around 6 heat sinks per heater. And that would provide an adequate amount of area for the heat to transmit effectively. Next, if we could go on to the coolers, Abraham.
Thanks, Khalil. So to continue the climate control, the same system was used as the heaters. So for the coolers, we have the same effect. So we have a cold side and a hot side. The way we did it was we calculated the amount of heat that was needed to be removed within the system. and that was calculated to be around 26 watts. And so we did the 15-minute time slot to see how much heat it would generate during those 15 minutes. And we did the energy gain from the environment, which came out to be 14.81 watts. And so the power that we ultimately would have needed inside the system for it to properly cool down the system, the same mass and specific heat of the weld plates, the air, and the assemblies inside the system were used. But this time we used the delta T difference because we wanted to go from 20 degrees Celsius to 4 degrees Celsius. So that in turn provided us with 84,000 joules in energy. So if we added that to the energy gain from the environment, we got around 97,000. And if a single cooler was able to provide 23,000 joules, we calculated that the value was 4.2. So we would need 5 coolers in total. And so with the 5 coolers that we have, we decided to do the convection coefficient and the change in temperature under the heat to get the area. And since the coolers were smaller, we got an area of 10 inches squared. And since we use the same off-the-shelf heat sinks, we got a value of 3.8. So that meant we would need 4 heat sinks per cooler. And as Khalil had said, we have the polyurethane cut out on the top of the system. Since the coolers would have the cool air sink to the bottom, we have a thermoelectric adhesive attached to the top where you have the fan in the inside and the heat sinks that match the Peltier cooler to be able to generate the amount of power needed to cool the system down. And we calculated that if we use the 5 coolers, it would take around 417 seconds or 6.5 minutes in total. So next slide.
All right, so the shakers use 2 NEMA 17 motors to produce, one produces linear motion and the other one produces orbital motion. When you combine these, you can get the 3 specified shaking patterns: linear, orbital, and double orbital. These motors, at the very end of their spec sheet online by the manufacturer, they can produce 20 Newton centimeters at a little over 1100 RPM. This correlates to a maximum mass of 7.5 kilograms that could be on the shaker table, but we can't think of any scenario where anything remotely close to that would be placed on top of it. But this torque is still useful in improving the angular acceleration of the cell wells and the conical tubes that are placed in the conical tube rack that you could see above, that black box with holes drilled in it. The conical tubes will be placed inside those, and the diameter of the holes drilled in the bottom are too small for the conical tubes to fall out, but this allows the light to shine through for the ODFI measurements. Next slide.
All right, so now we're on to our gripper subsystem. So the gripper subsystem is primarily a linear actuator, a vertical linear actuator that translates into horizontal motion. And so we see in this bottom right-hand picture, we have 2 L-shaped metal, this is aluminum construction, but 2 L-shaped, essentially metal claws, and they are pushed out and drawn back in upon the motion of the vertical linear actuator. You see they're connected and pushed by this trapezoidal aluminum block. And if we look to the left side of the bottom left picture, we'll see that drilled into this trapezoidal block is 2 ball studs. And the ball studs essentially travel down a drilled out channel in these claws. And so that's what's keeping the sliding motion going. And then also to ensure that they're moving in a straight line, there are 2 milled out channels on either side of these claws that make sure the motion is purely linear, back and forth in a horizontal line. And then on top of all this, this whole gripper system is mounted to a linear action, or a vertical stepper motor system. Now, this is an off-the-shelf component that basically allows users to attach components to a linear actuator, essentially. And how it works is it just has a stepper motor and a lead screw, and basically this allows our gripper system to lower farther down than our pipette and our ODFI, allowing us to easily grab well plate lids as well as well plates and conical tube racks without interfering with anything. As far as the calculations for this, the heaviest weight we would experience in our environment is a fully loaded conical tube rack, which comprises of 3 50 milliliter tubes and 7 15 milliliter tubes. And so we've got our weight breakdown here showing that the rack plus the lid plus the total liquid volume equals 1,621 grams. And doing a simple sum of forces equation, we see that the normal force needed would be about 2.05 pounds. And our gripper is able to supply that on both ends, just splitting the force, because we have a linear actuator rated for 4.5 pounds. And just to note, I'm not sure if it's quite visible here, but we do have 2 rubber pads on either side of those L-shaped grippers to ensure a good amount of friction between the weld plates and the gripper themselves. All right, next slide.
Hi, my name is Alex Kuchalakis. I was in charge of the gas injection system. The premise behind our gas injection system, we figured that it would be a 1/4 inch NPT hose connection. So we used these solenoid valves with a 1/4 inch NPT connection. Based off the manufacturer's ratings, these are safely rated for all of our gases. So no explosion should occur, and they should not fail under a maximum of 520 PSI. Using that rating and like known atmospheric pressures, we were able to find the volumetric flow rate coming out of each of these solenoid valves to be 67.421 meters cubed per minute. Our volume of our entire system is only 0.314 meters cubed. So this would easily allow for the environment to be filled under the 15-minute mark that was allotted. We also use a gas analyzer kit to analyze the amount of each gas inside the system. So if any gas were to leak or need to be seen how much gas is inside the system, we can see the percentages there. And our Raspberry Pi will also be able to control the solenoid valves and how long they're open for. We also have seals made of plastic to prevent any sparks inside of the solenoid valves. And then we use these 2 fans pictured here to allow gas to come into our system and then get mixed sort of like a blender in the system and then pushed in to the different densities of the gas. Thank you.
Good afternoon. My name is Cameron Anderson, and I'll be discussing the optical density and fluorescence intensity system. So the LED light array that was pictured earlier includes amber and white lights. The amber lights are for ODFI sensing, and the white lights are for the photobioreactor. And underneath the clear table, these lights will provide an underglow for our photoelectric sensor pictured here to be able to measure the optical density. And on the side, there's a calculation for how far above the well plates the sensor must be. So the sensor measures the light at an 11-degree incident angle, and based on the diameter of each well on the well plates, it needs to be 9 millimeters above to be able to measure each well individually. This sensor is on the same linear actuator as the gripper, and there is enough clearance so that there's no interference when the system is measuring. And as pictured during the shaker system, the conical tube racks are custom made with holes in the bottom to prevent light from passing through the sides with the clear racks, so that way we can effectively measure the ODFI for the conical tubes as well. So we can move on to the next slide.
Right, so here are just some additional views that we'll use to answer any questions at the end, but we can just skip through these additional views of it working. And these are the customer needs maps where we took each customer need, derived a quantitative metric for it, found subsystems, and linked it back to the subsystem features. We could go through all these maps for every subsystem, but that would be quite tedious. So instead, we would just like to tell you why we think the UC GAMs should be selected for prototyping in the next semester. So first off, the UC GAMs is cheap. It's under 75% of the $10,000 limit specified by the customer. So unforeseen costs in the prototyping stage, everyone knows when you prototype, stuff doesn't work out, stuff needs to be replaced, stuff needs to be modified. We have a great cushion to provide for these modifications while still not meeting that $10,000 range. The UC GAMs is simple. Each subsystem is pretty independent, so when things inevitably need to be changed, if they do, during prototyping, these will be easy to implement. And it's effective. It meets all customer needs except for need 17, which is contains each well plate in a different environment. And it does process up to 30 conical tubes at a time, or 3 well plates at a time, or any combination of the two up to 3 different types. So we'd like to take this time to answer questions.
Hey guys, this is Tom Singer from Northrop Grumman. Good job. I want to like commend you. At the very beginning of the presentation, you gave an excellent walkthrough of how your system operates and what exactly it does. That's I would say the best, but I could also say the only team that has given anything that really gets into the, how your system is intended to operate. So good job. I don't know if you were talking to other people and slipped that in at the last minute, but I'm real happy to see that.
Thank you very much.
No problem. A couple of things on your heating and cooling time. You had, I guess you based that on 15 minutes to get the environment up to temperature and down to temperature. Is that correct?
Yes. So we took into consideration basically the loss or the gain of energy from the environment based on our insulation, and then we took into account the air, the well plates, and the other assemblies inside of it with their specific.
And I see for the well plates, you've got a mass of the well plate, which I assume is the mass of the dry well plate, right?
I believe it is full.
Oh, is that full? Okay.
Yes.
Because it's going to be mostly full of water, I would guess, right? And I think I saw on a later slide, at least for like the tubes, you've got 255 grams of fluid in the tubes, and that should have a CP of about 4,000 or so joules, right? So I think maybe you're undershooting the thermal inertia of your system. And I would also say, if I were the customer, I would write a requirement that says I want the temperature of my sample to, hit 70 degrees in 15 minutes. I don't particularly care what the temperature of the air is. I care what the temperature of my my little beasties are. So I think that's going to add a little bit of time, or the way you guys are doing it, that's going to add a little bit to your energy requirements. I don't have a good feel for how much. It's not a ton of fluid, but it is going to be a little bit. Let's see. You've got a measurement of your dispensing accuracy when you were talking about your fluid handling system. There's something like, what was it? Like a tenth of a microliter. Is is that reasonable to expect? Is the accuracy of your linear actuator there the only thing that is going to impact the precision with which you dump fluid into a well plate?
So for the precision, we decided to do a calibration curve so before assembly, we're gonna test the amount of fluid dispensed per step of the motor. And from that curve, we would use it to address the precision requirement of the system.
Okay, just you know, I don't have a biological background, but I can imagine, you know, just from the surface tension of whatever media that you're putting in, you could wind up with a drop of fluid on the tip of your pipette that doesn't, you know, fall off in, and that's going to be way more, I would expect, than 1/10 of a microliter. So that might be a little misleading on that count. I could be wrong. Again, I don't have a ton of experience there. On the same system, you'd mentioned that you've got a friction fit for all of your disposable pipettes.
Yeah, so how the system works is there would be a O-ring on the nozzle of the system, and the whole system will move down into the new pipette tip rack, and a friction fit. It would be pretty much friction fit with the nozzle in respect with the pipette tip diameter.
How many cycles of pipette on, pipette off do you expect the O-ring to last?
We haven't considered that, so we would that's a calculation that we would need to address.
Okay, yeah, that I mean, I don't have really any good metric for how long that would last, or could even come up with a way to calculate it, but it's something I'd be interested in. And on your shaker, can you switch over to your shaker system? A couple of questions on that one. All right, so from the CAD model that you've got in the upper right-hand corner, is the motor that's doing the linear actuation, is that sort of rotating constantly, or is that just sort of a back and forth oscillation on the motor shaft?
Are you talking about, so the upper right photo, are you talking about the motor on the left or the right?
On the left. Right where your pointer was kind of what I'm looking at. I'm seeing a cam that's going to interfere with the shaft of the motor if it's rotating, you know, 360 degrees.
Yeah, it would have to be pushed to pretty much the very tip.
Okay.
Yeah.
Yeah, that I don't know if you can spec a shorter shaft or you know, relocate the motor in there, but that's something to consider. And then I'm wondering, what are those vertical posts? Are they supporting that top plate somehow?
Those have rounded tips that you can't really see because the table's in the way, and it does support the table.
So the table slides on top of those rounded tips as it's being moved by the two motors?
Yeah, the table legs are stuck in the bottom of the structure, and those are fixed, and the table slides on top of them.
Okay, that without any sort of bearing or anything, that's just.
It would have to be lubricated every once in a while. Same with the bottom of the motor.
Okay, that's an awfully long cantilever, and you know, I don't know how much of the weight of the system would be resting on those, but it seems like an awfully long cantilever to want to be putting a oscillating load at the tip of. I've been asking other teams about natural frequencies that they'd be exciting with their shaking system, but in this case, I'd be concerned specifically about fatigue at the base of those shafts where they mount into the table. That seems like a dangerous design, I'll say.
Yeah, now that you mention it, it would be a lot better just to have panels instead of those, a more solid frame than just 4 cylindrical supports.
Let's see. The one other thing I'll mention while I kind of have the floor, I really appreciate you. You know, when you're showing your costs and you're showing, you know, we're at like 65% of the budget. I appreciate you framing that in terms of like a margin on cost. You've got a prototype design and recognize that, you know, as you know, get into the you know, actually building your prototype, that you're going to find things out and see room for improvement and room for things to change. Most of the other teams are, you know, they're right at that 10K budget. So if something's got to change, you know, they don't have any room for adding costs to fix problems, and you guys do. So I appreciate that.
Thank you.
Thank you.
Okay. We've got about 15 minutes left in the time block. You guys finished a bit early. So if there are other questions from the panel, we can entertain those now.
I'd come up with a couple more.
I can also speak to that question you were addressing about the pipette tips. A quick solution we could do is to present the customer with, a whole bunch of O-rings and basically say to replace them after a couple of months, because the O-rings are very cheap. And that's just a quick budget solution we could do. The O-ring material was Viton, which is supposed to be very wear resistant and chemically resistant as well. But just that's something we could do if we were to move forward with this.
Okay. While you're on that picture, are you? It looks like you've got a linear actuator that's offset from the axis of the plunger on the pipette. Is that correct?
Yeah. So what I'm not sure we quite talked about it yet, but if you do see towards the top, there is a shaft with a collar on it. Yeah, right there, the laser pointer. So the way our device works is, as the reason it's offset is because it needs to travel down and eject the pipette tip. So basically, we have a calibrated volume of 1,250 microliters that the syringe sucks up, and once it's past that point, and like on the way moving down, once it's already ejected the 1,250 liters of volume, it will keep moving down per instruction of the user interface, or like a control system. It'll keep moving down, and that collar will press down on that 3D printed plastic part you see there, and that will essentially connect with the lip of the pipette tip, pushing it off of the nozzle. And the nozzle,
your ejection and your fluid dispensing, I guess, is all part of the same motion?
Yeah.
Oh, that's clever. I like that. The reason I was kind of asking that is, with that off-axis loading, you're creating a little bit of moment in your structure, right? Are you reacting that anywhere other than just the plunger tip inside of the body of the pipette?
Not really. We probably need to think about that in the future. When we were designing this, we were kind of just looking at things on like in scale of, oh, this is only the 5 millimeters. It seems very small. So that was kind of what we were doing with that, but it would probably create some moment that we should take into consideration. One thing to note is that bracket is as wide as it is to fit flush on the front and back panels of that plastic enclosure. So it kind of acts as a guide rail system. So that's something to counteract the moment, but it might cause some issues.
I mean, if it rotating that at all, I think is maybe.
It's definitely something.
Okay, something to think about.
Yeah.
Your gripper system. Can you flip back to the gripper? I like the gripper.
Sure.
That's a clever gripper. I see you've got these little balls in the slots and nuts on the face of them. What is your friction situation there?
Well, the friction situation there was not analyzed. The intent was that the user would have to lubricate with oil prior to each major experiment, or at least every few major experiments, because that probably would be an issue over time.
Right. Yeah, I would guess that whatever retaining nut that you've got on there isn't really designed to slide on things. I would think something, some sort of bearing would be called for there.
Okay.
Yeah.
Gotcha.
But it is an interesting system, and I like that it's got some capability to grab a lid, grab a well plate. So I like that. That's a neat design. And then on the ODFI system, can you flip back to that? Okay, cool. I'm not sure I understand the height that you're calculating here. Is this based on like an ability to like see the entire diameter of a 384 well?
Yes, so it's based on the height to measure one well at a time instead of it sensing more than one well.
Okay. So if you're within 9.4 millimeters and you're centered over the well, then all that this sensor can see is the area of that one well?
Correct.
Okay.
Yeah, I think we have a picture of it back there scanning, just so you can see like the clearance. Yeah, there it is. So that pipette tip would be ejected after it's done dispensing, and so that ODFI sensor would for sure be the lowest thing in the vertical plane. So it should have no problem. I mean, it could touch the well plate if needed, but it needs 9 millimeters clearance.
How many cycles of fluid handling and ODFI measurements do you expect to have? In what is this, a 20-day, 30-day experiment? I forget what the customer expect.
We really don't know. I mean, we were given a bunch of different needs for a whole bunch of different customers. So I mean, we're intending it for it to be whatever the customer needed. I know some customers didn't even really care about cell evolution at all. They were just kind of doing one-off experiments, and some were super into it. So yeah, we're not entirely sure how often the customer would want to cycle these.
Okay, but in a situation where I guess where it would be acceptable to reuse the same pipette tip, except for the fact that you've got to get rid of it to do your ODFI measurements. I guess that's kind of where independent height control of the two systems would come in handy.
Yeah. It definitely would be good. We opted to go for this just to keep it simple. If there were, the more motors we add, the more chance there is of things going wrong, really. And the cost too. So unfortunately, that's a downfall of it, I guess.
Yeah. Okay.
Okay. So we do have about 6 minutes left in the session. We also have a 30-minute break after the session is over. So we can wrap early if we like, or if the panel has more questions, we can continue for a few minutes.
I'd like to stay and take questions if there's more. Pointing out things to consider makes students better practicing engineers in the future.
Has Dr. Nemi beat you guys up over using 80/20?
Surprisingly not, but we've been told that we
really.
Yeah.
Oh man, I thought he got everybody with that one.
Well,
I don't know that. Have you guys?
Yeah.
Oh, sorry, Devin. Have you guys interacted with Dr. Nemi in a design review? You might have just avoided him. But if you did, I probably mentioned, but maybe more gently, the need to. Well, and they, to be fair, they did give in the beginning. I think that slide was particularly focused on what if Dr. Nemi asked about 80/20, but because they gave a pretty good rundown of why. But I'll let you guys answer, imagining that Dr. Nemi is here. Tom's question about why 80/20.
I guess I'll go for it. Yeah, I mean, the two primary reasons were one. Okay, so we tried to limit. We know 80/20 is not the best, and we tried to limit the moving parts to be.
Can I ask, what do you mean when you say not the best?
Not the best in terms
by what
of,
metric?
Sure, in the metric of after a while things start to get loose on 80/20. That's its biggest downfall. So
Okay.
the components that, especially with regard to motion, so the components that we used 80/20 for, if you notice, we have like 3 brackets on every corner, which is definitely overkill, but that was in an attempt to reduce the possibility of those fasteners becoming untight. Also, those horizontal bars that support the guide rails, those are actually drilled. No, the lower ones, those ones move, but the ones below them are stationary. Those ones right there, those are drilled into the side of the 80/20. So at least the part that is supporting a lot of weight, that is drilled in the side. In addition, there's also brackets on there. But again, the one of the main reasons was because it's easy for people to assemble, and this is a large container. It weighs about 110 pounds too. So we want them to be able to assemble it quickly. And then also all of our components along here, the bars, they slide on rails. So to cheapen the cost, we would have to manufacture rail systems and manufacture grooves in every single bar. So that made it cheaper. Yeah, and those are really the two biggest reasons we went for it.
Okay, so you're anticipating quite a fair amount of assembly, right? Because if you're shipping somebody a case that's disassembled, then every system that they're buying, they're going to have to install within this case as well, right? Is that something that is feasible? I mean, if we're talking about, somebody may not have the skills to do something more than, put T-nuts into slots in 80/20, are they going to have the skills to hook up electrical and cooling systems as well?
Well, luckily for them, we are assembling an instruction manual in our final design report, so that'll hopefully help. But as with regard to the coolers, I'm not quite sure really how they even connect. Maybe Khalil or Abraham, if you guys have knowledge on that.
So
yeah, I mean, 20.
Packaging for assembly is a whole other thing. If you look at you buy products and what comes assembled and what is expected for a user to do themselves, I would assume you could package a Peltier plate, glued onto a heat sink like this, and that's something they don't have to assemble, but maybe they have to connect wires or plug. It looks like you've got a little plastic connector there that can be plugged in, unplugged. So that's a whole other level of thought of what are you going to expect the user to do to put this thing together.
Yeah, being quite honest with you, the electrical part of the heating and cooling wasn't greatly considered. So yeah, that would definitely be something we'd have to look more into in terms of assembly and shipping.
Yeah, perhaps if this design were to move forward, we could include some sort of wire train or some sort of pre-assembled package, kind of like a wiring harness in a car, something like that the user can just plug and play. Like say all of those heaters were daisy chained to each other. If they just had to plug in one component, actually, really, I mean, if the components were able to just plug in, I think that would probably alleviate most of the problem, especially, yeah, I think so. But
yeah,
definitely something we
yeah. I mean,
consider.
You're definitely offloading a significant amount of effort onto the end user. I don't think, I mean, it doesn't seem like folks' manufacturing costs have been very significant. So it seems like the only thing you're saving the user is having to move around a completely assembled unit, especially with as far under the cost requirement as you guys are. So that may be something, you know, rethink whether that's a necessary thing for your end user. And also bear in mind that all of your competitors are providing them essentially fully assembled units.
Right. Okay.
This can be shipped, and in the customer needs, it said fit through a doorway, which our system does. I believe the longest requirement is only 40 inches by 30 inches deep by around 25 inches tall. So it can be shipped fully assembled, but we thought the customer is going to assemble it themselves, as one of the customer needs in the customer needs statement we were provided was easily moved by one person when disassembled. So we took that as it would be shipped in parts and the customer would be assembling it wherever they were assembling it.
Yeah, I remember seeing that need, and I think they also had a max weight of something like 600 pounds or something to fit on the table. So yeah, clearly, you know, if something's coming in that heavy, that's not something that can be moved by a single person. That's one of those customer requirements to me that I would, you know, go to the customer and say, hey, can you explain exactly what you're envisioning to do here? I've mentioned in other reviews, customers are often, you know, they're very good biologists and biological engineers. They're not professionals at writing requirements. So sometimes they need a little hand-holding.
Thank you.
Okay, well, so on that note, we're now definitely at the end of the session. So I want to make sure that we're sensitive to everybody's time, and give the panelists a 30-minute break, which is built into the schedule before we visit with the last two groups. So we'll wrap it up there. I want to thank. Sorry, this was group 3, right?
Yes.
Yeah.
Yes.
Okay. I'm like looking at the wrong number. So sorry, it's getting late in the day. I want to thank group 3 once again for sharing with us your design and spending your afternoon with us. We really appreciate all this hard work and creativity. And hey, you guys are almost done, right? Just one more assignment to go. So almost to the end of 4501.
Thank you for joining us. Thank you for having us.
Yeah. Thank you.
Yeah, thank you.
Thank you
Thank you
guys.
so
Good
much.
job, guys.
All right, very good. So let me stop recording.